Good morning, everyone. I'm going to make a video, possibly a YouTube video, if I manage to figure out how to do it, um, about the pandemic COVID-19 and the ever popular flatten the curve scenario that's everywhere in the media. And I would like the folks to understand how it works, how to flatten the curve. And I'm a mathematician, so I'll try my best to explain it from fundamental principles. Okay. So if I can invite my wife that is videotaping me to focus on the paper, please. And I'll try to explain the scenario. So I'm going to explain this fundamentally on a very simple model, but yet that captures the idea. Is imagine you have a pandemic, COVID-19, going through a society like a tsunami wave. Everybody will eventually get infected, and it's going so fast that the people who get infected remain contagious for the duration of the pandemic. You can put that into a question, but fundamentally, I would like to use this model to explain the ideas. Okay? So if you can kind of focus on these are the curves that are being flattened, and I would like to explain what it means to actually flatten them and why do they flatten if we try to reduce the contagiousness, i.e. implement the restrictions in society. Okay, so let's take a moment to take a look at the fundamental relationship that is happening. So the rate of infection of people in a society is proportional to three things along the way. R value is the contagious value of the virus. So some viruses are fairly contagious, some are less. This COVID-19, this evil thing, has about 2.2 or 2.5 folks being infected by one person at any given time. Anyhow, back to the model. R is the contagious value, and clearly more contagious it is, faster the infection. Current population infected, P infected, so more people infected, more they spread it, that makes sense. But there is one thing that sometimes that's forgotten. As more and more people get infected, then there are fewer and fewer people to be infected by the infected people because everybody is infected pretty much already. So there is also the factor 1 minus P divided by K, and this is kind of the mitigating factor to slow down the infection rate past the peak. Anyhow, so that's the fundamental idea, fundamental model, and I would like to explain how it works to flatten it by reducing the R value. So the maximum rate that's going to happen is when half of the population is infected. It's kind of intuitive, smack in the middle. When half of the population is infected, we got the maximum rate of infection. So if we put P to be K divided by 2 into the formula here, we're going to get, basic algebra, we're going to get the peak rate, which is a quarter of the R value times K, which is the total population. In Canada, we have about 30 million people. So that's the peak. Okay. And then we're going to figure out how wide is the pandemic. So i.e. how long is the bulk length of the pandemic hit. So if everybody gets infected, if you could kind of focus on this thing here. If everybody gets infected, so the K value is fixed, so 30 million, this is the peak rate. And the area is fundamentally, I know it's not a rectangle, but it looks like it quacks like a duck. It's a duck, so it's going to be the peak times the width is going to be the same value, K. So if the peak is a quarter of R times K, then the width has to be about 4 divided by R. So bigger the R, smaller the width, smaller the R, bigger the width. Okay, so then at least we have an idea that the peak and then the width, and last but not the least is the time it takes to reach the peak. So as the R value gets reduced, then time kind of dilates by the factor of R, or 1 over R I should say, so it takes longer to get to the peak. So you can think of it as a time slowing down and it takes longer to get there. So these fundamental relationships that we have are going to guide us into flattening the curve. So to wrap it up, I have an example here, and then we have a situation where it's 2.2 contagiousness value, and we have a curve that's going to be high. Now the 16 here would be, well, 16 is kind of middle of the way, so to speak. So we got a lot of people being infected at the peak, but it's a small width following this relationship. So then if we manage to reduce the R value, the contagiousness, by a factor of 2, we implement some restrictions in society, then we're going to halve the value for the peak. So it's about 8 something. So we're going to halve the value for the peak, but make the width twice as big as a result. So it will last us twice as long, the hit of the pandemic, had it been the previous value. High peak, small width, smaller peak, bigger width. And then if we divide this by 4, i.e. we implement even more draconian measures, we're going to quarter the peak for, and a little bit, so 4 million per unit of time. So we are quartering the peak, but then we're going to multiply by 4 the width that it takes. Anyhow, so I would like to summarize this thing. So as a mathematician trying to explain the fundamental ideas, is that yes, we can actually indeed flatten the curve, and we have these linear and reciprocal relationships. Again, if you halve the contagiousness value, implement restrictions, you're going to halve the maximum peak, so the hospitals can expect half of what it would have been if we didn't do anything, but we also expect it to last twice as long, the hit, so to speak. If we do it 4 times, then accordingly the same thing. So anyhow, so thank you for your attention here, and I hope it kind of makes sense. And these are not Gaussian bells, by the way. They look like it, but it's not really that. It's a little bit more complicated logistic derivatives, so to speak. Thank you very much.